All right. So the first portion that we are going to look at this week is going to be about temperature and heat. All right. These are the two main sort of characters that we are going to focus on during this first week of class. All right. So I'm going to talk to you about what does it mean by thermodynamics and what does it mean by thermodynamic system. The key is, why do we need this? All right. You have been tortured so much with the Newtonian physics already. Why you still add some more pain to this with the thermodynamics? All right. And the main characters is temperature. We're going to talk about this one more time. Then what does it mean by temperature, even though we are all familiar with temperature? We make measurements every day, even during the right now with the COVID time, we make measurement of our own body temperatures even more. All right. But what does it mean from the physics perspective? It doesn't have physics. It doesn't have to be physics perspective. It is temperature since the beginning, I think. All right. And we're going to talk about some laws in thermodynamics. Talk about this. That's a weird one. The zeroth law. This is the only things that physicists can do, right? You don't know where to put this law in. You already defined the first, the second, and the third. So you found this law to be like super fundamental and so important. So you squeeze in as a zeroth law. That's so weird, right? This is the way that physicists think, I guess. All right. And once we're done with that, then we'll have a chance to look at some application or some, something that we can relate to, which is the effects of the change of the temperature. We're going to take a look at the thermal expansion and how can we take care of those. Okay. And once we're done with that, then we'll take you to a little bit further in terms of look at matters, right? What kind of things that you can talk about. And of course, when you say want to talk about from the physics sense, you should be able to have some way that you can calculate them properly using some relationships and things. So we're going to talk about the gas. That is the good system that we can use for learning stuff. And when we have that built in, then we're going to end this week with the heat. What does it mean by heat? And have some, introduction to that. And we can talk about the specific heat. All right. And that will be on Saturday. All right. Sounds good. All right. So let's finish up today's lecture with what it means by thermodynamics, temperature, the law of temperature, the law of thermodynamics and all this stuff. Okay. First thing first, why do we need these subjects at all in physics? There's the word dynamics in here. And you have done a lot of dynamics from the Newtonian physics. You learned sigma F equal to ma. You did force, the momentum, energy, impulse, and everything. You already has done that from physics 101. But now we have more dynamics for you. And this one is dealing with thermal. So this means it has to do something with thermal stuff. And this is what we want to talk about now. But what does it mean by thermodynamic system? So I would like to start the whole thermodynamic stuff with this question. How many oxygen molecules are there in this, let's say in my room right now? Can you approximate in this, my environment right now? How many oxygen molecules I'm breathing in, I exhale the carbon dioxide, whatever, but there are O2 lying around here for me to breathe and everything. What is the numbers that we are dealing with at this point? What do you think? Approximately, of course, I don't know exactly, but we should be able to, all right, how much or how many? Hey, I forgot to ask, is the voice and sound and everything come out fine? Is that clear and sort of like, no problems? Yes? Okay, great. All right, just don't hesitate at any time if there are any technical difficulties, just let me know, all right? Because I know listening to, lecture that sounds really bad, that's super bad and it's annoying, it's a painful experience, all right? Don't want to have that. Okay, so how many guys, approximately, what do you think? Whew. Just kidding, just have some. So that's a rough number. What do you think? You give me an order of magnitude, 10, 100, 1,000, million, something like that. So what do you think? Rough number. What are we dealing with right now? How many oxygen molecule around me right now at this point? Okay. Any participation at this point? All right. Okay. That's okay. I can answer it myself. Okay, so what do you think? All right, now, that's a first, all right, entry here about what, 10,000, 10,000. Okay, so I will write it down like a 10 to the fourth, 10 to the fourth. All right, anybody else want to try? It's getting there. Million, okay, here we go. Billion, okay, very good. So now we're getting higher. Billion is like 10 to the nines. Okay, very good. Getting higher. Anybody else? Want to get more, gonna get higher. 21. I meant 25th. Okay, that's fine. All right, 10 to the fifth. 21. All right. Oh, wait. There you go. 10 to the 100. This is like, wow, that's way too big, guys. Oh, that's unimaginable numbers. Oh my God, hundreds of zeros. All right, 10 to the fifth. All right, very good. All right, so if I write these numbers down, how do you feel? How do you feel? Have you seen this before? Ah, okay. Have you seen this? I think so. From somewhere, chemistry maybe. Yeah. So this one is Avogadro number. And you can use like the capital N with the subscript A, say it's an Avogadro number, right? So this one is the same number as a 1 mole that can be converted to 1 mole of gas molecules or atoms. Yes. Isn't that only like 10 to the 80 atoms in something like that? Well, 10 to the 80 maybe, I'm not so sure. It's maybe even, yeah, that's possible somewhere. I don't know. Haven't checked. All right. But 10 to the 100, that's like way too big. But is that a Google? It's like Google 10 to the 100 or 100 to the 10? I don't know. All right. But anyway, the point is you have seen this number before, 10 to the 23rd. Right? And there's a factor in the front about 6 times 0.2. That is a mole of gas. So when you say a mole of gas, mean yeah, that's whenever you talk about gas in the system, you should have about that much amount of gas, 10 to the 23rd. So that's a million, and 100,000 more approximately. All right. So that is the number that we have to deal with in this room if I am interested in gas that is flowing around. Okay, you guys following me right now at this point? Second question. Hey guys, can you give me the kinetic energy of the oxygen molecule? Can you do that? Well, Ajahn, that's not too bad. You just set up like a super sensitive camera detecting the velocity of the oxygen molecule and then just do 1/2 mv squared. You should be able to get the kinetic energy of that molecule. So that's no big deal. That is fine. Third question. Can you find me the total kinetic energy of the oxygen molecule in this room? Can you? Hmm. That's getting harder. Why? Even though you know that this relationship is good from Newtonian physics, 1/2 mv squared, there's nothing wrong with it. But do the summation of that big of a number somewhere near Avogadro number, you have to do this summation million times. That means you have to do million observations of the velocity of those molecules. Who are going to do that? No one have a chance to do that. Even though you have like a super duper camera that are able to, like, you probably need tons of cameras helping each other, detecting all the velocity and everything, plug it into the formula. You even have a harder time to, sum them up. You might need like a supercomputer and all this stuff. And then don't forget, those molecules will knock each other all the time. So all of those velocities will be changed over time. So you're not going to be able to answer this in real time because velocity of those billion molecules will change all the time. So my question is, can you answer this? If I persist, I'm insisting that, hey guys, I need this total kinetic energy of these molecules. I want it. Will you tell me that this is an impossible question to answer? And here comes the thermodynamics. It turns out I can give you the answer. And the answer is so simple. Take the temperature measurements. Whoa.
Okay.
Isn't that cool? So I don't know if this one give you like a some sort of like some perspective into thermodynamics study or not, but that's what it is. The thermodynamics come in to our picture when the Newtonian physics hit some block, hit some, some wall that it cannot be applied. It's not because the theory is wrong. It's not because 1/2 mv square expression is not applicable. No, it's just because the way that you want to get to the final answer is just too much to do. Okay, too much to do straightforwardly from the Newtonian physics. That's all. So that's why we need some other way to deal with this kind of system. And this kind of system that is called thermodynamic system. You guys with me now? All right. So this one come hand in hand with the idea of statistics. Every time you talk about the statistics, that's when you don't want to deal with the detail. Well, of course, I mean, you deal with the detail, of course, but you come up with the way that you can represent the whole population using some parameters. For example, if I want to know, hey, what is the average age of the population of Thailand, of Thai citizens, for example, you are actually in reality, you can go, knock door by door, asking for the, what's your age, sum everything divided by the numbers of, populations and everything, you get the exact number. But in reality, you're not going to be able to do that because it's too much to do. So all you do is that you use statistics. You maybe do some sampling, you do something, and then you use statistical methods to, approximate or at least come up with the average age of the population. Same thing over here. The T that you are seeing over here, the temperature, is like statistical parameter. Is the average, is the single parameter that you can use to go back and explain what is going on from what kind of things that going on in the populations. In this case, the populations is oxygen molecules, billion of them. Okay, sounds like sort of like things that can be done here. I don't know. I give you like enough sort of like, introduction to the thermodynamic stuff, but this is the stuff that we are trying to move away from microscopic calculation. So we don't want to deal with the velocity. No, I don't want. It's too much. It's too detailed. I want something that is macroscopic. That's the whole thing. That's what we want. Temperature is easy to measure, right? And you don't have to set up a camera. You don't have any like speed camera, super high speed camera, nothing. Just make temperature measurement, and eventually you will be able to tell, hey, what is going to be the total kinetic energy of the gas in this room? Believe it or not.
Okay.
So that's super cool. Okay. And that lead you to the introduction to the temperature. So now we kind of a little bit, get the connections. Temperature actually eventually will lead you to total kinetic energy of the system. That is what the temperature is about. Okay. And we sort of familiar with temperature for a long time because we have thermometer. We take a measurements of the coldness and the hotness of metal, of material, of substances, everything using thermometer. But what does this thermometer is doing? What it's doing is this. You can think of this like this is a substance that you want to make a measurement. You want to take the temperature of this, and then you have the thermometer. Of course, the thermometer will have its own temperature. That objects that you want to make a measurement will have its own temperature. What you do is you take these two objects, put them in contact. Put them in contact. However, at first, they might have totally different temperature. With me? But once you put them in contact, there are some things that are about to happen. And that's where the dynamics part is about. Okay, you guys with me? So dynamics is some movement is going on. But right now, the movement is going on due to thermal effect, due to the temperature difference. So over here, that's why we define the word of thermal contact, guys. This is it, thermal contact. So every time that you have two objects that you are taking different temperature objects and put them in contact, that's going to be a thermal contact. That's kind of straightforward over there. But then after that, if you wait, there will be some exchange going on that we're going to study. And eventually it will stop moving. And that means you have already reached thermal equilibrium. Sounds good? All right. So I hope you see the contrast between what we are doing here and what you did before with the Newtonian physics. Now, back in the day, remember when you have this, okay, you have a box, you push, yeah, maybe you apply some force, F, on and on, yeah. You notice that nobody cares about the temperature of this dude. Nobody cares about the temperature of the box. I don't care. Okay, it doesn't matter to me. I don't care. But now, from the context of thermodynamics, you might have to ask, well, Ajahn, wait a second. Maybe my body temperature is 37 degrees Celsius. The box may be already sitting at 25 degrees Celsius. So that means once my hand touches the box, there should have some dynamics going on at the point of contact. That dynamics that happens during this contact, that is thermodynamics. Sounds like a good term, yeah? No, that's the wrong one.
Okay.
All right. Okay, so I hope that is the introduction to thermodynamics. It's the dynamics stuff that's caused by temperature difference. And now we know the temperature is actually the representatives of total kinetic energy of the system. Cool. All right. And that summarize everything under zeroth law of thermodynamics, the weird one. So what they say is, let's take a look at this one. If objects A and B are separately in thermal equilibrium with the third one, then A and B are in thermal equilibrium with each other as well. I think this is common sense to you guys now, because you can imagine of the third one to be thermometer. So that means if you take object A in touch with the C, which is thermometer, and then you put the object B in contact with the thermometer, object C, but then they read the same reading, they give you the same readout. Then you can say A and B are at the same temperature. So that means if you put A and B in thermal contact right there, they are already in equilibrium. So that's it. They're gonna just like sit there and doing nothing. Okay, sounds good? All right, so just talk about this one and just move on. So what the conclusion that can be made here is just the zeroth law of thermodynamics is just the expression or description they're talking about the thermal contact and thermal equilibrium. That's done. Okay, cool. All right, so that's, we don't have to worry about this anymore. All right, and before we take a halftime break over here, to be able to sort of give the readout, we need some units, and we have some scaling and everything. So I mean, the unit of temperature that we are familiar with is going to be Celsius. Okay, and because we studied this topic using water back in the day, we didn't know the atoms, we don't know the structure of material, we don't know much. So that's why we study water, and we say, okay, water changed the phase to ice. Okay, let's call this 0. And then the water changed the phase to steam or vapor, then call that 100. And then we have scale from 0 to 100, something like that. All right. So that was the like a arbitrary. It's not totally arbitrary, but at least relying on the property of water. Okay. However, what we want to use is the absolute temperature scale in physics. That is SI system. Okay. The Celsius is not, the absolute temperature scale is. All right. And I am going to talk to you about this. What does it mean by absolute temperature scales after the break? Sounds good? All right. So that's what happens. So we're going to take a 10 minutes break in between. All right. So that will be good. So we're going to do the absolute temperature scales after the break. So see you, I think it's 11. All right. Sounds good. All right. So take 10, guys. See you in a bit. All right. So what is the absolute temperature? Yeah, that's the question.
Okay.
Now, even though this is from the textbook, this is the experiment that sort of showcase how can you sort of like extrapolate what does it mean by the absolute temperature scales. And from the perspective of maybe for those of you that has already taken chemistry, they say that, hey, if you talk about the pressure of the gas, and then if you reduce the temperature down, the pressure of the gas will getting smaller and smaller and smaller. And no matter what type of gas you're talking about, eventually it's going to reach a single point. And they name that point to be at absolute temperature. Is when the pressure is supposed to go to zero. Okay, cool. Nice. But I would like to give you another approach of this one. Let's imagine this. Imagine that if you are looking at one single particle in the universe. Oh, there you go. There you go. All right, let's say this is a only single particle in the universe. Nothing else. It's blank vacuum, nothing. And this particle doesn't have any internal structure. Oh, the sound is unclear. Okay, give me a second here. Oh, me too. What's changed? Was it unclear the first half as well? No. It's been like this? That would be bad. Oh, it was fine. I haven't changed anything actually. What happened? Okay, so let me adjust my microphone a little bit. Okay, let me double check if the mic is from the USB. Okay, so is this better? Yes. Hello. Oh, that's weird. Or maybe just the angle. It was just a little bit too high back in there. Okay, maybe I have to talk directly into the mic. Sorry, guys. Okay, so is it good now? It's good. It's good. All right. So now back in this. So the vacuum is nothing. That's nothing. I have one single molecule, no internal structure. That's nothing at all. Okay. Now I give this some energy, like burn this. Of course, which doesn't make sense. I shouldn't be able to light like any fire in the vacuum. But anyway, the point is I can just shine the laser light into it or something. I don't know, shoot it with the laser beam on and on. The key is I give this particle an energy. I'll give it an energy. So let's say somehow I throw an energy to this. All right. In this case, what happened to this particle, guys? What do you think? It's only a single particle in the universe. And somehow it obtain an energy. What can this particle do with the energy? I assume it would move. Very good. Actually, that is a very good assumption. Correct. So the thing is, there's not much we can do because it has no structure. There's nothing there. So it's going to move. So I gave it some velocity vector. And when it moves, that means it's going to carry some kinetic energy, 1/2 mv squared, correct? Now you see what I'm seeing right now? So what I'm saying over here is, at first, when it has nothing, it has no energy. That's when you're talking about zero absolute temperature. With me now? And then when it has some energy, it has to travel. When it moves, it has kinetic energy. So every time that there is some kinetic energies, that means the temperature must not be at zero anymore. So it's still the same relationship that we did before. Temperature telling the amount of kinetic energy of the system. Okay, so absolute zero, that's when there's no movement. Everything is just stationary. Okay, very good. And thank you. So what is the unit of this absolute temperature? We name it Kelvin. So every time you talk about the absolute scale or Kelvin scale, they're meaning the same thing. They are absolute temperature scale. Very good. Okay, cool. So now in conclusion, what does this point means? It means, of course, if you are at zero absolute temperature, all of the gases in your system won't move. So when there's nothing move, there's nothing knocking on the wall, When there's nothing knocking on the wall, there will be no pressure that you can measure from the wall. So that's why pressure goes to zero, because of no movement. With me, guys? All right, so that's it. So that's an easy connections between temperature and kinetic energy again. Higher temperature mean higher translational kinetic energy. Okay, simple as that. However, I just want to talk about this right now. It turns out, that's a weird thing, the 0K is impossible in this universe. That's too bad. So nothing in this universe actually is stationary. It somehow has to wiggle a little bit. It has to move a little bit, or at least up to our knowledge, or something that we can deal with under quantum theory and everything. Nothing is perfectly stationary. So that's why 0K is an impossible temperature to attain. Okay, so that's just so you know. And actually, that is a part of the third laws of thermodynamics, saying that 0K is impossible. All right, but we're not going to deal with that too much. So I'm just going to say it right now. Okay, so the relationship between those two scales that we mentioned, the Celsius and Kelvin, the absolute scale, are related through just a linear translation. So if you have temperature in Celsius, you can convert this one into Kelvin simply by adding this number to it, 273.15. Or in our case, we can just use 273. That is good enough. Okay. But the good thing about these two scales is the scaling are actually at the same stepping size or the same resolution. What I'm saying means the change of the temperature, I use the delta, all right, the symbol delta. The change of the temperature in Kelvin is going to be exactly the same as the change of the temperature in the Celsius scale. So that's a good thing. So that means increase in 1 Kelvin will be the same as the increase in 1 Celsius. All right. So as long as you are dealing with just the change in temperature, you can use either scales. They are they give you the same amount. Okay. All right. So that's a good thing. But you will see that in the future, you will need the value of the temperature. If that is the case, that temperature usually most of the time will be in Kelvin, in absolute scale all the time. Okay. There is another scale that is still being used right now, is Fahrenheit. And I think maybe the only US is using this scale at this point, so we don't need to worry too much. But you can convert between them if you like. There is a conversion equation that you can. But I think just like a fun fact, the Fahrenheit and Celsius scales read the same numbers when it's at 40 below. So it means at negative 40 Celsius will be exactly the same as negative 40 Fahrenheit. All right. Just for fun. But the thing is, the change in these two scale will be different now, right? They are not separated by 100 from 0 to 100. It's not going to be the same thing as 0 to 100 in Fahrenheit, on and on. So that's kind of weird stuff. All right. But we're not using it. So don't worry about it too much at this point. Okay. Who came up with the Fahrenheit and why? Actually, that's a very good question. I don't know. All right, I'll look to it. All right, that's a good question. Never asked before because maybe it didn't cast too much. That's bad. That's maybe my ignorance here. All right, but anyway, that's a good thing. Anybody knows? Yeah. All right, I'll look it up. That's sort of trigger my curiosity as well. Thank you for the question. Very good. Okay. All right, now, so here comes the things that we're going to be able to talk about now. Then what is a consequence of changing the temperature of substances? All right. So what happened when things get hotter? And now we know hotter means higher in temperature. And now we know even better that when you have a higher temperature mean higher movement. So when there is a higher movement, mean you have higher kinetic energy and all this stuff. Okay. So those are the connections that you can go from the temperature to the energy, mainly kinetic energy. However, in reality, things are complicated like this. Some molecule is not just like a gas molecule. It's not like a single molecules and all this stuff. So what you have over here is just, you're going to get, on average or on the big picture scales, what you can think of is just like, hey, things are moving more when things are hotter. However, we can only talk about this one in some matters. in some kind of simple material, because nowadays you guys know we have like super weird composite material, the materials that made from some weird combination of stuff, so they can exhibit kind of like super duper characteristics and other stuff. So if we talk about just the substance that's simple enough that we can relate the temperature to the direct movement of the molecules inside, then at least what you can think of is like you're going to get some expansion every time that you increase the temperature. Does that sound reasonable? Okay, so think about this. If you are in the room, like jam-packed, so with your friends and everything, right? And then it's like, let's say shoulder to shoulder, for example, right? You're standing. And then the room's just like, let's say air conditioner in your room is just like, got broken. And then, the room getting hotter. Of course, you're going to get like annoying a little bit when people just, stay too close to you guys. You see my picture, right? And then you just say, hey, can you move a little bit further away? And so, it's feeling hot right here. Just stay apart as much as you can. So you get the idea of the expansion. When you get hot, you get annoyed. When you get annoyed, it's like you move more. It's just, don't want to stand still and everything. So the same thing as molecules. So when molecules getting hotter, the temperature is higher, it moves more. So the spacing between molecules tend to increase. And when you zoom out in the macroscopic scale, then, all right, the whole piece of that substance get expanded. And that comes down to the thermal expansion. Okay, sounds good? All right, so that's simple one. But of course, if you want to look at the scale of the change of the temperature, it can go as crazy as this one. The lowest temperature achieved, I mean, nowadays, I think it's now down to nano Kelvin now. All right, so it's sub nano Kelvin at this point. You can get as close to zero as you want, but you won't get down to zero. All right, and then move up a little bit, you get liquid helium, liquid hydrogen, liquid nitrogen. Okay, this one is more common because you can use that to make some ice cream and all that stuff. All right, so this thing is around like, let's say 77K or so. All right, and then you move up to water freezes. We know that water freezes at 0 degrees Celsius. So when you add 273 through this one, you get 273 Kelvin. So at around 273 Kelvin, that's when you get ice and water mixture and all this stuff. All right. So the scale is somewhere around 200, 300. That's now down to everyday's, room temperature is about 300K. All right. And then when you move up to the surface of the sun or the melting point of copper, now you're talking about almost hitting 1,000 Kelvin. Right, it's getting higher and higher. And then if you look at above the surface of the sun, you have some corona going on, the activity on the surface of the sun. Now you talk about 1,000,000 Kelvin. All right, and if you look deep inside the sun, you have like the nuclear reactions and things going on. That's 10 million Kelvin. And if you look at the center of the hydrogen bomb in the nuclear bomb and everything, so the temperature can go as high as 100 million Kelvins. All right, so those give you like a grand pictures of the scaling of the temperature. It's about like, almost like 9 order of magnitude coming from 0K. Okay, all right, but what we are probably dealing with is going to be somewhere around here, like hundreds of K. Okay, that's where our room temperature is about. Okay, so how can we take care of this thermal expansion? Once we know that there are some temperature changes, so what we have is a simple equation that can explain this expansion. When they say simple, you guys look at this equation, how do you feel? That's kind of nice and cool. Okay.
Okay.
It's just like, okay, Ajahn, it's a linear equation. There's no square, there's no square root, there's no weird function that you have to deal with. The delta L over here gives you the change of the length. So start with like a piece of metal, piece of a simple substance. Let's say you start with the initial length of L naught is showing up right here. And somehow you warm things up and then you make a measurement again. So the length of this one get larger. That change in length, you use the delta L for that. Okay, cool. And now you can say that the delta L should be proportional to the initial length. It depends on, what is your initial length of this piece of material. And it should be proportional to how high of the temperature change. You heat it too much, not too much. I mean, you heat it, how much you heat it up. All right. And the last thing is you probably want to know, like, hey, how good is this substance in thermal expansion? So we define a constant to indicate the ability of this substance to expand. We call this the coefficient of expansion. However, because right now we're looking at just the length, is one dimensional right now. So we put the word linear to it just to signify saying that this is a single dimension expansion that we are interested in at this point. Sounds good? All right. So this equation is simple to use. Change in the length, it depends on the coefficient, the initial length, and what is the temperature change. All linear terms. Very easy to apply. Okay. All right.
Okay.
Oh, there's a question. Oh, there's an answer here. Thank you. Daniel Gabriel Fahrenheit. So probably that will be the guys that invented this, or sort of started this Fahrenheit scale. Thank you. All right. So we'll look it up further. All right. All right. Next. So that alpha, the coefficient of linear expansion, is listed for some materials in this table right here. Okay. So as you can see on the left, it's just going to be material that looks sort of common. It's just like metal, maybe aluminum, copper, some glass, some lead, some concrete, and all that stuff. All right. So we are not talking about like super weird polymers or some composite material that behaves something weird. All right. So this is just simple substances. And all right, on the right, these are photos that give you some consequences of the thermal expansion. When things expand, they have a tendency to push each other, and then things get broken and everything, like a railway over here. That even though every time when I look at this one, and I know that engineers forgot to leave some space between those railways and all that stuff to take care of the expansion during the hot summer day and all that stuff. But it's still always confusing why, I mean, the projects team seem to finish and everything is being used already, but then the railway just got gone bad, maybe due to the climate change, maybe. I don't know. All right. So it's just like why this problem didn't show up during the construction time. I don't know. Right. This is still unsure. All right. But this is like historic photo. Okay. All right. So with that, now you're probably wondering about that. Wait a second. What you just looking over here, that seems unrealistic, because in reality, this height has to expand too. And the depth over here has to expand as well. Why you can only care about this? I mean, I'm not only care about this one, but this one just give you an idea how can we explain the expansion that happens. All right. But over here, but yeah, you're right. The expansion must happen in all directions. So it might be better to talk about the volume expansion, not just only the length expansion. So that's what we are going to take a look at. Now, guys, take a look at this equation. How do you feel? That's a weird question. How do you feel? When you look at this equation, it's like, Ajahn, they look exactly the same between the previous one and this one. They're all linear. The change of the volume depends on some coefficients, the initial volume, and the change in the temperature. So good. They are still linear anyway. And we can name the beta to be coefficient of volume expansion. That is fine. Okay, well, so what's the point? The point is this. Actually, we can get to this equation by taking the equation that we created for a single dimension and combine them into a three-dimensional expansion. And this is going to be the first sort of like mathematical things that we do today. Here we go, guys. Stick with me here. All right. I don't know how do you like this sort of mathematical expressions right here, but it's not too bad. All right. Stick with me here. Start with this. So the initial volume at initial temperature T0 is going to be the length, the width, the height. Okay, so there's no big deal. Let me do the color coded here. So we have the length, the width, the height. Okay, now I increase the temperature. So the temperature rises by delta T. So that's no problem. The length will expand. No problem, yeah? So the delta L is right here. And from the expression from the linear expansion, it's just going to be alpha L delta T add on top of the initial length L. So that's good. That is the new length after change of temperature. Now move on to the width. The width will do the same thing. That will be the alpha times the initial width times the change in the temperature add on top of the initial width. Same thing will happen to the depth or the height. Alpha h delta t, that will be the delta h add on top of the original height h. Cool, so far so good. Now, that means the new volume after change of temperature is going to be, here we go. You look at this one, but I can pull some common factor here. L is there, I can pull it out here. W is here, I can pull it out here. H is there, I can pull it out there. So no problem, I pull common factors out to the front. What I'm left in the parentheses is gonna be 3 of the 1 plus alpha delta t. So this is what I have left here. You guys with me so far? Nothing new, haven't done anything much, except now you're probably wondering, Ajan, I'm having the cubic function right here. How come the final equation doesn't have any cubic terms at all? Can you see that? Yeah. Every time you talk about volume is always like a cubic stuff. But how come these are all linear? And here comes the thing. How do you feel again? How do you feel? How do you feel about this expression, guys? 1 plus x to the n is approximately equal to 1 plus nx. Have you seen this before? Maybe. Maybe. No, very good. If not, let me show you something that might look more familiar to you guys. If I write this, 1 plus x squared, it's going to be a complete square, which is no big deal. This one is, yes, better. I can do more. 1 plus x cubed is going to be 1 cubed plus 3x plus 3x squared plus x cubed. Yeah. Better, feel better. Let me do one more. 1 plus x to the 4th is going to be 1 plus 4x plus 6x squared plus 4x cubed plus x to the 4th. On and on and on. Yes. All right. So this is just a polynomial expansion of 1 plus x to the power of whatever you're liking. But then the thing is, imagine this. If my numbers x over here is just a small number, bear with me here. Let's say, let me give you an idea. If I put x to be just like 0.01, so this means it's just 1% of 1. So what you have over here is, in the second terms over here, the numbers that show up from here will happen on the second digits after the decimal place, right? It's on the second decimal places after the digits. Yeah, sounds good. All right, so that means the first terms here will already push the number down to the second digits. Okay, all right. Then when you look at the square term, this one will link you to x squared, which is 0.0001. So whatever numbers shows up here is going to happen on the 4th digits right here. With me? And it's going to get even pushed further if you look at the x cubed. The x cubed over here will push this number down all the way to the 6 places over there. On and on and on. So let's say if I say, hey, I think I'm okay with just 0.01. I mean, I would like to keep my accuracy down to only like the second digits accuracy. That's all I need. I don't need like the 4th digits. I don't need the 6th digits. I only need the second digits. So all I do is just, hey, I'm just going to cut this whole thing off. I don't want anything anymore. I'm just going to leave just the first linear term in my expression. You guys with me now? And hence, this is the final thing, saying that every time that you have 1 plus x to the n, and if the numbers x is not that big, you can just keep the linear term and throw away the higher order terms. For those computer engineering, computer science people do this all the time, this is the linearization of the thing. Because you don't like square term, you don't like cube term, because in computationals, doing the square, doing the exponential, everything takes a lot of CPU time. So everything's, if it's linear, it's just adding numbers. It's easy to do. The process will be fast. Okay, sounds good? All right, this is only when x is less than 1. Yes, correct. Because we want x to be a small number. And the reason this one works, because you guys look at the alpha. If you go back to our table right here, there you go. See, all right, it's gonna be quite small because it's, yeah, it's all like to the -6, blah, 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 right? It's pretty small. All right, so it seems like it works really well. So that's why I can just use this approximation and then turn this cubic function into just a linear function. I can approximate this dude to be just 1 plus 3 alpha delta t. And that's it. I'm done. So this is the term of the change. The change of the volume can be written in terms of just a linear function. And now you can notice right away, well, Ajahn, I can see this 3 alpha. Number 3 come from that cubic power over there. So the 3 alpha is here, and that is our beta. So that's why every time that if the expansions can happen in all 3 dimensions in the exact same rate, we can say that beta is going to be always 3 alpha. And we call this type of material that the expansion happens equally the same in all directions to be an isotropic material. All right, but this one just like a fancy word saying that any direction, they all look the same. Okay, the isotropic material. Okay, so that this material expand in all directions in the same rate. Okay, cool. All right, so that's it, guys. So why do I sort of like spend so much time talking about this? It's like, well, Ajahn, why don't you just like quote the equation and be done with? Why do you have to go through showing you the approximation and everything? Because I just want to show you that this equation that we are facing that right now is not a law in physics. You see what I'm saying? So the point is, you have sigma F equal to ma. That is exact. That is like you have to use this. Every single object has to follow this equation. You cannot, come out of this without using this equation. But this is not. This equation is just equation that you try to use it to explain the expansion behavior or expansion phenomena using just a linear function. So is this exact? No.
Okay.
With me? It's just like an approximation. You can see right away, if you are like a super fine engineer and you want like, hey, I want the super accurate calculation, you need to include the higher order term, something like that. Okay, so I hope this gives you an idea. What I'm trying to get to is just like, hey, this equation is not that important as like sigma F equal to ma. It's just like equation that allow you to explain what does it mean by thermal expansion in the numerical sense. Okay, cool.
Okay.
All right, and that concludes things. How to use this equation, that will be exercises. All right, so we move on to the, before we move on to the exercises, I think there's something that worth noting. If you notice this table here, and if you look at the number of the coefficients of linear expansion between steel and concrete, yeah, that's kind of nice. You can see that these two numbers are almost the same. And that's good because we use the steel reinforced concrete to build this skyscraper or buildings and everything, right? So you want these two materials to expand and contract during the day and at night at the same rate. So, otherwise then the steel will pop up on the concrete with cracks and everything. So that's kind of engineering that has to be some, concerned about this kind of thing. All right. And it's expand quite a lot actually, right? So a fraction of percent that worth a lot for the building that is super high, like tens of meters. Okay, cool. All right.
Okay.
So let's practice a little bit. If we want to approach this from calculus.
Okay.
All right. Otherwise, if we don't have any calculus, then that won't be like a physics course, right? Okay. So this is a calculus with no extra charge here to you guys. Okay. So I can actually do this expression using a little bit of calculus, just a little bit. For example, it's easy to look at this one by looking at, if you write the volume as, just think of it like a cubic, yeah, a cubic function. So you have the length of the cube, length L, and then you do the cube of that. That gives you the volume. Now you say, hey, I want to look at the change of the volume with respect to the length. Okay. All right. So what you want is you just want to take a look at the dV by dL. Okay. And that will give you 3L squared. Everyone still remember this calculus, right? Okay. So that's the wrong sound effect. Okay. So now you can write this one as a differential form. So that means the change of the volume is going to be dV over dL times dL. That is a chain rule. And then I just plug 3L squared right here in the front. All right. But then you say, hey, what is the change in the length? You already had this relationship over here. This is the delta, is like a big change. But you can turn this one into a super mini change by taking just a mini change to turn it into a differential change. D alpha, I'm sorry, that's the alpha and the D look the same, sorry. D of the L is going to be alpha LD of the T. There you go. Isn't that cool? All right. So every time that you do this, that actually is getting it even better, because every time that things go super duper small, then this is pretty much an exact relationship. All right. So that means I can write this DL to be alpha LDT. All right. And once I have that, then I can just regroup a little bit. Okay. Let me take that L square, group it with the L, and write it as an L cubed. And that means you take back the V. And as you can see now, the 3 alpha pop up in the front, just like what we had before using the approximation. And once we have this, we can turn things back into a differential form. And that's it, you're done. Okay, sounds good?
Okay.
All right, but this one just for fun. I mean, you don't need to worry too much about this derivation or anything, but just, just want to mix in some calculus. Otherwise, then it's not physics somehow. Okay. All right. Move on, guys. So this is just for fun. But the good thing about having you to seeing this allow you to extrapolate or interpolate. What will happen if you're looking at the two-dimensional sheet? Then you can guess right away. Oh, Adan, by using the same techniques, either the approximation or either the differentiation, you can say that for a two-dimensional sheet of material, the areal expansion, the expansion in area, is going to be 2 alpha. Okay, so now you sort of give like a grand structure. If you look at the one-dimensional expansion, it's going to be 1 alpha. The area, you have 2 dimension, it's going to be 2 alpha. If you have volume 3-dimensional, it's going to be 3 alpha. Okay, sounds good. All right, so that gives you the whole structure of this linear expansion stuff and extend it through the volume expansion. Okay, guys. So this table gives you the value of some, materials and the beta of some material. So these are usually being used for liquid and gas. Right? So because liquid and gas, usually it's hard for you to measure the width, the height, and the depth. So they quote the volume expansion right away with using the coefficient of volume expansion beta. All right. So there are some application of this one that we can relate to, and that is the thermostats. Oh, right there. Okay. So in the thermostat, it's very clever actually. They use different type of metal, in this case, brass and steel. And because brass expands more than steel, so every time the temperature change, then the brass will expand more and bend the whole bimetallic piece, right? So bimetallic, there are 2 types of metal here. All right, and once you have this kind of sort of behavior, then you can attach this bimetallic strip into a switch, for example, and then you can use this switch as like a sensor, or as like what they say thermostat is the switch that turn on and off depends on the temperature level. All right, so this is a good one. But I don't think you guys see much of this anymore, because nowadays we use electronic stuff to control temperature. So yeah, but I think there are some applications that electronic might not work. For example, in some environment that is super hot, for example, that electronic might not survive there. they might still depend on, physical stuff. So there are some uses there. Okay, but for household items, probably nobody use this anymore, I guess. Okay, all right, guys. And just to confirm before we move on to some final exercises of the day, well, this equation is not like law of the universe. So that's why there are a lot of exceptions. And the one exception that's so obvious to you guys is water. Water has the highest density at around 4 degrees Celsius. So that means if you're sitting at 4 degrees Celsius, no matter you cool the water down or warm the water up, the water will expand no matter what. See? So that's already,
Okay.
yeah, this equation won't work universally anyway. Okay. So just, yeah, at least just give you an idea how can you take care of the way that you can explain the thermal expansion in a simple case. You can use that, linear expansion coefficient. You can use volume expansion coefficients, and that's it. All right. But this is not going to work for all cases. Okay. All right. Just make sure that you guys remember this. Okay. So let's do a quick exercises here, and then I think we can wrap up today's lecture with this couple of exercises here. First one, if you have two spheres made of the same metal, having the same radius, one is solid and one is hollow. Whoa, okay, so one hollow, one is solid. So what do you think will happen when you take these two items and move up in temperature? Are they going to expand the same, different? Which one is supposed to expand more? What do you think? The hollow one or the solid one should expand more? What do you think? Just kidding. Solid expand. Okay. Oh, they're both. Okay, you have two. Okay, two answers come in here. All right, here we go. Just want to make sure that you sort of get an idea. We talk about, some approximation. Let's think of it like just a linear approximation. If I'm were to be one of those molecules inside this metal, okay, as a molecule myself or atom, I'm not going to be able to tell what happens million atoms away from me. You guys with me? If I am standing here, let me do the red one. That's me, the red one. I'm not going to be able to tell million atoms away from me, there's no more atoms, so it's a hollow case. Or millions of atoms from me, there are still more atoms to look at. So overall, what I can feel is just whatever happens around me, just neighboring atoms. So what I'm saying over here is, to me, I'm just going to push all my neighboring atoms out, no matter it's hollow or solid. Does that make sense? I don't care, or I don't know. I mean, maybe I want to care, but I don't know. I don't have any information of that. So by having this idea, it seems like they're supposed to expand at the same rate or at the same amount. Okay, because microscopically, I'm not going to be able to tell if this piece of material is hollow or solid. All right. So the way of thinking about this one is just, you can imagine like you're doing a Photoshop. If you have like a photo, and when you warm it up, it's just like you blow this image up. That's it. That's what I'm doing right now. It's like you are expanding it. So you expand the whole piece. That's what I'm saying. Okay. So that's what the thermal expansion is. So that's why if I'm asking you this question, if I have a piece of metal and I cut a hole in the middle and I warm this piece up, put it on fire, what will happen to the hole? Will the hole get larger, smaller, or no change? What do you think? Yeah, the hole shrinks, right? You will feel that. Now, I'm going to erase this hole. Instead of cutting a hole, I'm just drawing. Put a drawing that has the same size as the hole. And now I burn it, raise it at the same temperature change. What will happen to this drawing? Yeah, correct. See, so actually, if you go back to the hole, then based on my argument, the hole is supposed to expand as well. You guys with me now? Okay. All right. So that's what it is. So in general, what I'm saying is no matter there is a hole or not, if I warm it up, the whole piece will expand. The whole piece will expand. So the hole will expand along with it. So it's just like you starting with this piece and then you're doing a Photoshop, you do the expansion operation and then everything just get larger and that's it. Okay. So the hole will expand along with the whole piece. All right, guys.
Okay.
Good? Okay. So the next exercise is just showcase how easy it is for you to use the expansion equation. So you have an aluminum tube, 3 meter long at 20 degrees C. What is its length at 40 degrees C and at 0? All right. So this is easy in the sense that you can look at, just write down the expression delta L, the change of the length is going to be the alpha of aluminum. All right. You can look it up on web or on the table and everything. Multiply by the initial length, and then you do the delta T. All right. The point of this exercise is just to showcase that the delta T can be positive or negative. So if you warm it up, the delta T will be 40 minus 20 degree. And that is going to be positive 20 degrees Celsius change. However, if your delta T is negative, that is fine. The final temperature is 0. Oops, sorry. Final temperature is 0 and initial temperature is 20. So it's negative 20. So this equation works either it's positive or negative. Change happens to the delta T. Okay, sounds good? All right. So with that, then you can get to a new length. The new length is going to be the original length plus the delta L. And that's it. So that means in part B, it's going to shrink a little bit. All right. In part A, it's going to expand a little bit. Okay. So don't be afraid to use this equation in either the positive sense or the negative sense. They work both ways. All right. It's linear equation anyway. Okay, cool. All right. Okay, last one, guys. I think this is the last one of the day. And we're going to take a look. It's kind of weird why it takes a lot more time today. Oh, no, that's the wrong one. Sorry. It's supposed to be like down here. All right, guys, try this one. You have the concrete sections, all right, of a certain superhighway and are designed to have a length of 25 meters. Now the sections are poured and cured at 10 degrees Celsius. What minimum spacing should the engineer leave between the sections to eliminate buckling if the concrete is to reach 50 degrees Celsius during the daytime? Okay, so this one is not bad because the whole idea is you pour and cure the concrete, and then you're supposed to leave some space between section there. Okay, and that's what you want to figure out. What should be this minimum spacing? Let's call it X. Okay, what should be the X over here? And of course, because this is just like a freestanding concrete block, so when things expand, it's supposed to expand equally on both sides, just to be fair. Okay, so you can imagine that whatever delta L that you calculated from your equation is supposed to, let's say, half of this go to the left and the other half go to the right. Sounds good? All right. And of course, this expansion will happen on the other piece of the block. So there will be a contribution of the delta L over 2 coming from the neighboring block. So over here, then you can say that the minimum spacing X is just going to be just the sum of those two expansions, and it will give you back the delta L anyway. Cool.
Okay.
All right. So all you need to calculate for this problem is just, hey, what is the delta L of the concrete section? And then you are done. That will be your minimum spacing that you need to leave as well. Okay, try that. So delta L is just alpha of the concrete times the initial length. Okay, let me put that one in right away. Oh, I hit the black button again. Sorry, guys. So that is the initial length of this one, and that is 25 meters. So let me put 25 meters right here. Cool. All right, now you multiply this with the delta T. The delta T is going to go from 10 all the way to 50. So the delta T will be 50 minus 10 degrees Celsius right here. Cool. All right, and that's it, guys. Once you look up the value of the coefficient of the alpha, for the concrete, plug it in, and you are done. That's easy enough. Cool. All right. So you can finish the numerical calculation yourself. All right. Sounds good. So far, so good. All right. Is this doable? I hope it's not too bad. But things will get worse over time. This is just like, introduction lecture. Okay. All right, guys. Last one before we leave. All right. Just to make this at the same stop as the other section. So let's finalize today's lecture with this. And I don't know you like this or not, but this is like it's non-numerical question. So it's the analytical question. You have a liquid has the density rho. They want you to show. So good thing is you know what you need, right? You need to show that the fractional change. When you have the fractional change, mean the change with respect to the original, right? You want to take just the ratio between them. In density for a change in temperature delta T is given by this expression. And what does the negative sign signify? All right, you want to try this? Kidding. Okay, so how are you going to approach this? So instead of talking about just the volume, you want to talk about the density. Okay, first thing first, you have to know what was the density before. Right, okay, John, that's used to be like this all the time. The density is just mass per unit volume. So that's no problem. That's fine. Okay. But now what you want is just the change of the rho with respect to the temperature. So you say, okay, Dan, I know another one we just learned today that the volume change is going to be the beta times the original volume times the change of the temperature. So somehow you want to make the connection from the rho all the way to the change in the temperature. How can you do that? All right, now I'm going to use the same trick again that we did. We're just going to use a little bit of calculus. Why not? Okay, because dealing with the delta is kind of tough because you saw that we need some approximation. We need some stuff that's kind of annoying. So I'm going to turn this one into differential change. Why not?
Okay.
Okay. All right, when you do the differential change, that's good. You don't need like an initial volume or anything. It's just a volume there. And then the change is going to be differential, super, super small. By having this in the differential form, now I'm going to look at this one in the change that happens in the differential change as well. Super, super small as well. So what I'm going to do is, I can see that now the dV is waiting for me here. So what I really want to try is I want to try looking at what is the change in the rho with respect to the volume. You guys with me? Because once I have that, then eventually I'm going to be able to link the dV down to the dt at the end. So what I can do is taking the derivative of this one will give you m is just a constant. The derivative of 1 over v give me negative 1 over v squared. Looks good? So far, so good?
Okay.
I can turn this into a differential form as well. D rho is just now negative sign is in the front, m is there, v squared is here, and dv is on the right. Whoa, and you can see almost done. Now I can just, here we go, drag this dude here, plug it in there. So what I can do is now it's just be equal to negative m over v squared beta v dt. All right, and one of the v get canceled. That's good. And that leads me back to negative v m over v beta dt. But of course, m over v is just the original rho. So this one is fine. So this is rho. So I can turn this rho to my left-hand side and combine this with the d rho on the left. So that's how I get d rho over rho. It's going to be just whatever left here on the right, negative beta t. And that's it. Oops, sorry, dt. And that's it. I am done.
Okay.
Cool. And of course, I can always turn this back into the delta if I want. It's just an approximation. All right. So what does the negative sign mean? Of course, Ajahn, it comes from the inverse proportional between these two, rho and the v. Yeah, see that? The rho and the v, they are inversely proportional. So that means when v is up, rho is down. So that's where the negative sign means. So the V is changed due to the change in the temperature. So what I'm saying is, it's a simple indications of the inverse proportional change. When the delta T is positive, the volume increases. The volume increases, the density decreases. And that's it. That's where the negative sign is signifying. Okay, guys?
Okay.
And it's done for today. Use all the time. Like that I have 50 minutes exactly. All right, guys. So I hope you learned something today, and I hope this gave you a sense of what's about to happen in the next 3 months or so. All right. So I think it's time for me to stop, and I'll see you guys on Saturday morning. Sounds good? All right. Bye bye, guys.